Schlichting, who is well known for a number of papers on QCD and kinetic theory and non-equilibrium quantum field theory. And tonight he will tell us about non-equilibrium green functions of the energy momentum tensor. Thank you very much.
Yeah, thank you very much. And first of all, since this is also the last talk, let me thank the organizers for really putting together such a wonderful workshop here. So as Michael just said, I will today be talking about non-equilibrium Green's functions of the energy momentum tensor. This talk will be somewhat more on the application side, so I'll also try to tell you for why these things are actually very useful, and we can actually use them to describe heavy ion collisions or certain aspects of that. And so this is mainly based on a particular paper with Yuka Mata, Maurizio Martinez, Philipp Plaschke, and Stefan Ochsenfeld, and also some earlier work in QCD. Okay, so how do I go? Yeah. Okay, so brief motivation. So of course, for me, the motivation to look at these things comes in trying to understand dynamics of heavy ion collision, which typically we model kind of by a hierarchy of effective descriptions of QCD, exploiting the fact that somehow we have different regimes which are well separated in the reaction dynamics. So the collision itself takes very short. Then there's typically a short non-equilibrium regime followed by a long hydrodynamic expansion and subsequently some kind of later free streaming into the detectors. Okay, and so the main idea here is that if we want to describe the whole thing, we should also care about these early stages where the system is out of equilibrium. And so we want to develop tools and techniques to describe somehow this early time pre-equilibrium evolution of the QGP. And then, of course, that's how it's related to this workshop. Also, how do we have the transition towards relativistic viscous hydrodynamics? Okay. So how do we usually look at this kind of pre-equilibrium dynamics? And there's, I mean, this has been a very active field of research, so to say, in the last, well, let's see, at least last 10 years or so. So there's been a lot of progress in terms of understanding this based on different microscopic theories. So typically we use microscopic theories to study these out of equilibrium systems. However, the way that we study this pre-equilibrium dynamics is often based on a number of simplifying assumptions. Okay, and so one of them is that oftentimes we look at actually almost all the time we look at a system which undergoes this so-called Bjorken flow. Okay, and so the picture associated with that is essentially that instead of somehow looking at the whole collision, you make an idealization where you say, well, okay, maybe let me just look at a small cell somewhere, say in the center of the collision, where then following the collision, that system will rapidly expand in the longitudinal direction, but somehow maybe in the transverse direction, it doesn't expand so much. So one neglects the transverse expansion at early times. And one considers the system, so to say, as somehow locally homogeneous and azimuthally isotropic. And so that's one of the kind of common assumptions one does in this type of studies. Now, the other thing is that, of course, the theories where we can actually do this kind of calculations is rather limited. So these are most of the times kinetic theories, Young-Mills or QCD kinetic theory at leading order, theories like the relaxation time approximation or using holography. Okay, and so the most well-studied examples actually somehow always involve conformal dynamics. And so these are kind of the two typical underlying simplifying assumptions that we use. So on the one hand, we kind of reduce the spatial dimensionality of the problem. And on the other hand, we consider conformal. Now, this is actually kind of a severe restriction, because if you look at this conformal Bjorken flow, okay, really you look at somehow macroscopic properties of the system, such as the energy momentum tensor, then for the conformal Bjorken flow, this really only has one independent variable. Okay, so the energy momentum tensor is just diagonal. It's also traceless for conformal theory. Okay, and thereby there's essentially one degree of freedom here in the problem. Okay, and you can kind of, for instance, choose this to be the ratio of the longitudinal pressure to the energy density ratio, which is somehow the most commonly studied example. Okay. And so, for that case, somehow the evolution has been well established in all of these different theories. What one typically finds, so here's an example of showing that longitudinal pressure as a function of the evolution time, even comparing different theories here in different curves. Okay, so typically what one finds is that, for instance, in the weakly coupled theories, there's a rapid initial memory loss. Okay, systems, different initializations of the system move towards a common curve, which has an attractor property, and then at some point on the order of essentially one equilibrium relaxation time, we can describe the system using viscous hydrodynamics. Okay, And so, so that's very nice, and that's also very useful, okay? Because then based on these kind of Bjorken flow attractors, we can also try to make certain estimates of, say, for instance, how the initial energy is converted to energy at the onset of hydrodynamics. And so even if you compare somehow different microscopic theories, what one finds is there's, so to say, 10 to 15% difference in the theories that these do this. So actually, even looking at very different theories, there's kind of a surprising degree of universality, if you want, so that these different evolutions in weakly and strongly coupled systems exhibit. Okay, and what you really care for in terms of phenomenology is how is your initial energy converted into, say, number of particles that come out, or the energy that goes into hydrodynamics, and that somehow is, I mean, that's essentially what's shown here. That doesn't vary very much between different theories. Okay, so. Now I told you that kind of in doing this kind of studies, right? We've also sort of enforced a high degree of symmetry, okay? And so despite a certain level of universality between different microscopic theories, one may then wonder to what extent these features depend on the underlying symmetry assumptions. Certainly, you can understand very easily that conformal symmetry here is important, but one of the things that you also realize is that, of course, trying to think about a homogeneous and isotropic system is perhaps not the best approximation of really the initial state in a heavy ion collision. And so neglecting this transverse expansion and considering homogeneous systems may actually be kind of a severe restriction. And so one would like to relax that and see if, well, these things still look pretty much the same. Now, to do that, well, okay, I mean, in principle, you could try to really fully break that symmetry, try to study all the microscopic initial state and the microscopic dynamics in fully fledged detail. That's in some examples possible, like in type of relaxation time, approximation type calculations. However, that's not what we are not what we're going to do here. So if you're interested in that, there's a few recent papers on that. What we're going to do here instead is that we will still break that symmetry of translational invariance and rotational isotropy in the transverse plane, okay? But we will do that at the level of linearized perturbations around Bjorken flow, okay? And so the essential idea is that, okay, in addition to somehow having our average energy momentum tensor, which only has energy and pressure components, we're going to have now, and this is the same everywhere in space, we're now going to have space-time dependent fluctuations, or space-time dependent corrections to that, which can have all the components of the energy momentum tensor and very essentially very arbitrarily in space. Okay, and so that's actually a useful concept. Okay, because I mean, if you consider something like that and you have your initial state, then indeed it kind of looks relatively lumpy. Okay, and so what you can consider is that okay, if you kind of parameterize your initial state as some kind of local average background plus some false fluctuations around it, then you can imagine that if you want to evolve it over the course of the pre-equilibrium stage, then you could do that by kind of dividing it up into a background, okay, plus fluctuations around the background, and the fluctuations around the background you would then sort of evolve with Green's functions in that non-equilibrium environment. So these characterize the propagation of these fluctuations, and you could kind of do time evolution in that way, okay. And so that's actually something that's actually formalism that we set up and put ready to use. That's called compost, and people have actually started to use that in phenomenology. Okay, so to describe the evolution of these, so to say, these kind of space-time dependent fluctuations, one has certain Green's functions for the energy momentum tensor. And of course, that's something that if you have a non-equilibrium system, you have to calculate from your microscopic theory. Okay, and so what was done originally is that these non-equilibrium Green's functions were actually calculated in a heroic effort, mostly by Alexas Mazurjauskas in Young-Mills kinetic theory, and that's what we put into this compost code. Okay. Now, what we did recently, and that's what I'll talk about in the following, is we calculated somehow these same non-equilibrium Green's functions of the energy momentum tensor in the relaxation time approximation. Okay, and the idea of that was to, of course, provide possibilities for maybe gaining initial analytic insights, which we didn't really manage to get so many so far, but also to check somehow for the sensitivity to the underlying microscopic dynamics, okay? Because at the level of just Bjorken flow, we have this high degree of symmetry, everything looks relatively similar, but what is if you break that symmetry, okay? So the setup we're considering is just the following. So we have a sort of a one-dimensional Bjorken flow type setup, but then we allow for fluctuations around this, and then we solve the Boltzmann equation in the relaxation time approximation, which is written here. So you have usual propagation, you have in the transverse plane, so we'll only consider homogeneous in the transverse plane, you have a longitudinal expansion, and then you have exponential relaxation towards equilibrium with a conformal relaxation time. We use the usual Landau matching, okay, and we'll take initial conditions which in principle land us directly on the attractor, so we shrink the support, the longitudinal support of the distribution to 0. Okay, so now how do we actually solve this? So the way we actually solve this then will be at the end of the day numerically, but nevertheless in the course of setting up this numerics, we I think did some maybe formally interesting manipulations. So we employ some kind of method of moments to transform this PDE Boltzmann equation to a set of coupled ODEs. So what we do is we take moments of the distribution, moments which correspond to something like the energy, but are then weighted with spherical harmonics. Okay, so for instance, so of different ranks L and M. Okay, and so for instance, the low order moment would be just the energy density. Then there's a certain moment of rank L equals 2, which would be the pressure anisotropy. And if you actually do this in the relaxation time approximation, what you find is that these evolution equations are closed at the level of just considering these energy type moments, so dimension 4 moments. Whereas in more complicated theory, you would actually have to also kind of vary the powers of momenta that you do. Now, for the particular case of Bjorken flow background, it turns out that the low order truncations of these moment equations correspond to ideal hydrodynamics. If you take the first non-trivial, only one moment, so to say, or three, no, well, the first 4 moments into account, okay. And Müller-Israel-Stewart type theories, if you go to higher orders, okay. And so actually, if you just consider the background evolution, then and somehow study some of these truncations, there's actually various analytic insights also into this. Okay, so what do these evolution equations for the moments then look like? So what when you work this all out, this is actually quite interesting, because what you'll immediately find is that, for instance, for the background evolution in the relaxation time approximation, you find that it actually, the whole evolution only depends on one conformal scaling variable, which is time in units of the equilibrium relaxation time, and you get some kind of coupled evolution equations for moments. So here C are our moments, the others are kind of algebraic coefficient, and then you have some relaxation of the moments towards equilibrium, okay? And then you can essentially perturb this system. We do this in Fourier space. Of course, we're perturbing around a homogeneous background, okay? And interesting, what you find is that, okay, carrying this all out and doing somehow a bunch of formulations, it essentially will still depend on somehow what is the age of your system in units of when it relaxes towards the system. But then there will be 2 additional dependencies. There will be one on, so to say, what is the propagation phase of the mode that you're considering. So K is the wave vector of the mode. Tau minus tau naught is how long has that mode evolved in your system. And it will also explicitly depend on the point of time where in the course of the non-equilibrium evolution you initialized your perturbation. So that's some point x naught. Now, of course, we are interested in the perturbation that was there at the very beginning, so we'll just set that to 0. Okay. And so while these equations, you can kind of, so for the background, you can kind of think about this. If I truncate this at some low order, I'll get a relatively small matrix that I'll have to, that's coupling these different moments, and I can probably get some insights. Things pretty quickly turn out to be relatively complicated once you go to this considering these perturbations. Okay, so essentially this is the evolution equation where you basically get some kind of terms which just describe you the free streaming evolution of these perturbations. Okay, and then there's various effects which somehow relate to somehow propagation, building up velocities in the longitudinal and transverse to your wave vector that you're considering, and also all kinds of other terms which describe, say, for instance, here the relaxation of your perturbations, but also changes in the background, in somehow the non-equilibrium evolution of the background, which would not be there if you were linearizing around actually an equilibrium state. Okay, so okay, after you get something like this, you conclude maybe this is too complicated to stay at first. So let's just get some numerical insight first. Okay, so numerically we solve this by basically just truncating this evolution equation at some kind of large value of the angular moments that we consider, and then we simply calculate these non-equilibrium Green's functions in Fourier space by basically looking at after some time what is the perturbation of the energy momentum tensor, starting with a given perturbation of the energy momentum tensor at an earlier time, okay, and so we normalize them to the energy density at the initial and final times. So if you were to do this around the static background, then this would be the same as this, and you wouldn't have to do this. But here, this has benefits if you look at say the long wavelength limit or so. Okay, so to somehow discuss some of the results, let me focus on a very simple, or the simplest possible channel, which is that initially we have an energy perturbation, so delta t tau tau, okay, in the limit where this perturbation was there at the very beginning, okay. And so what you find is that if you start with initial energy perturbation, of course, then you can write down essentially kind of a tensor decomposition of your Green's function. So there will be an energy response, there will be a momentum response along the wave vector, and then there will also be pressure and essentially a shear stress response, which somehow describe the spatial components, which will have an isotropic contribution and some contribution that's related to the direction that your perturbation is traveling. So what do these look like? Okay, so they are shown over here. So what we do is we kind of initialize the perturbation as in the limit that it was there at the very beginning, okay, and then we study how this Green's function evolved as a function of time. So that's shown here in terms of this color coding, okay. So initially, these Green's functions in momentum space kind of look like this. You can actually calculate them from free streaming. They're given by some kind of Bessel functions of different rank, essentially. And so then if you study, for instance, the energy response to an energy perturbation, what you'll see is that at low wave number, it will kind of slightly go down. Okay, then essentially this oscillation pattern tells you about what's the speed of the propagation of that thing. And then, of course, there's also changes in the amplitude of different modes as the system evolves. Okay, and so likewise, you find these kind of patterns in all the different channels: energy response, pressure response, momentum response, shear stress. Okay, so let's talk a little bit more about the feature. So I picked out here one particular channel, which is the pressure response. Okay, and so there kind of try to highlight three important features. So since we're perturbing this very anisotropic state, initially, actually, the pressure response, or the response of the transverse pressure, I should say, rather, is 1/2 of the energy density. Okay, and so as the system becomes somehow more isotropic, okay, so that goes down, okay. So eventually pressure becomes 1/3 the energy density, and so this kind of actually relaxes from 3/2 to 1. Okay, now as the pressure, of course, or the effective speed of sound, so to say, gets lower and lower, this also leads then to some kind of a change of the propagation velocity, such that kind of these peaks, which tell you about how fast your waves have propagated, how far these waves have propagated, kind of lead to shifts. Okay, and then also if you look in particular at somehow the behavior at large wave numbers, then you will always see that there's somehow a viscous damping of the short wavelength perturbation. Now, in terms of analytic insights, we don't really have that many. So there's some discussion. So what we kind of understand is, of course, this behavior here in the short wavelength and long time limit, where essentially you can again use hydrodynamics, and we have a sort of a whole appendix in the long paper that probably nobody has ever seen about this. Okay. Now, however, what I think could be interesting actually is if one kind of goes back to these moment equations, right? Then I told you that essentially this should correspond to some kind of Israel-Stewart-type hydrodynamic formulation if you truncate them at low orders. So I guess what one could do would actually be to somehow really look at what these different coefficients are, compare them with the hydrodynamic equations, and then really compare coefficients like what is the effective speed of sound squared in these evolution equations for the moments, and study essentially how they are renormalized, quote unquote, due to non-equilibrium background. Okay. Yeah. Okay. So then you can. So then what of course we set out to do in the beginning, right? We wanted to understand, somehow what is the microscopic sensitivity of this macroscopic response to the underlying theory. Okay. And so what we did for that purpose was to essentially compare all these different response functions between calculations in the relaxation time approximation shown with full lines, and in Yang-Mills kinetic theory shown in terms of these dashed lines, this time shown again at somehow 4 different evolution times. So let's focus maybe on something around 1. That's roughly where we would usually try to switch to hydrodynamics. And so generally what you see is, well, okay, if you compare, let's say, the energy response here, and there's similar results in all the other channels, you find that, well, there are some differences, okay, but essentially what's happening is that somehow in the relaxation time approximation, this kind of seems to be a little bit further ahead in the general trend of the evolution. So for instance, that green line here actually looks very much like that orangish line from the Young-Mills kinetic theory evolution, okay? And so overall, I would say that you find actually that the differences between essentially the Young-Mills kinetic theory and the RTA kinetic theory calculations are actually relatively small, and perhaps surprisingly small. Depends on who you ask, I guess. And it's probably not something that's observable really if you want to study, if you want to do phenomenology. Okay, so that was, so to say, the main part. So let me just flash some two other things that I thought could be interesting to think about and trigger some discussion. So, so as I said before, so we in that paper, what we looked at was essentially the behavior of perturbations in the transverse plane. Now, you may also ask, what about perturbations which actually happen along the longitudinal direction? Okay, and so in that case, it's actually interesting because if you think about it, initially your system has very small longitudinal pressure, so it's very hard for these modes to kind of propagate. On the other hand, the expansion is also very fast, so to kind of get gap a large rapidity interval, you want to push this. You want to see effects from the earliest possible time. So there's kind of an interesting competition between the buildup of the longitudinal pressure and the longitudinal expansion itself, which makes the propagation more difficult. Okay? So so one of my students in his master thesis, he actually went and kind of calculated this also in the relaxation time approximation, now including longitudinal perturbations. Okay, and so what you see is actually that the pattern in the longitudinal direction is manifestly different than somehow from the transverse direction. So again, for somehow the energy response to an energy perturbation. Okay, so here you see this kind of propagating behavior and viscous damping. Okay, whereas it seems that in the longitudinal direction, there is actually no such thing as really propagation here happening during this early phase. Right? It really looks like it's kind of just a sort of, I mean, function basically looks like a Gaussian here, right? So it looks like it's just some kind of diffusive behavior along the longitudinal direction. Okay, and then finally, one other thing that I wanted to flash here, which I thought could be interesting, is on this topic of Bjorken attractors. So I told you at the beginning that these things have been looked at in a number of different microscopic theories, including also Young-Mills and QCD kinetic theory. So in the recent work in the paper that's going to be posted on the archive this week, we actually looked at what happens in QCD kinetic theory. Okay, and that is interesting for one reason, because you have a theory which has multiple particle species, right, quarks and gluons, okay, and in principle their isotropization pattern can be different and can essentially occur on different time scales, okay? And so indeed what we found is that, so we did a bunch of simulations, so we looked at, say, the pressure over energy density ratio for different initial chemistry, so either all energy in gluons or everything in quarks and kind of all cases in between, okay? And so even if you started from kind of the same pressure anisotropy early on, okay, what you see is that there's actually kind of a longer remembrance of what this looks like, okay, and so I think what this is pointing towards is that somehow our picture, or well, having a picture where one has sort of a simple attractor that describes us the pressure evolution at early times, maybe somewhat too simplistic. At least we have to know something about the chemistry. Now, of course, this is this looks very much like this is part of a higher dimensional attractor curve, but to somehow know the pressure evolution, we would certainly have to know something about the chemistry also. Okay, and you find similar patterns also when you extend these calculations to finite density, which we showed here, which I show here on the right. So again, this is varying the amount of net baryon density. Initial anisotropy is essentially irrelevant, but going from low density to high density, you start to see different. Okay, so this then brings me to my conclusion. Okay, so what did I tell you? So I was trying to convey the message that non-equilibrium Green's functions of the energy momentum tensor around Bjorken flow, they are both interesting to study because they provide a relatively simple way of breaking Bjorken flow symmetries, but they're also of practical use in phenomenology. Now, the two existing calculations that we have, which are in Young-Mills and RTA kinetic theory, they yield comparable results, but I think so far we have sort of limited analytic insights into these objects. So I encourage everybody to look at these kind of equations and maybe find some interesting insights. as kind of a future outlook, of course, we want to include this, we want to extend this also to include all the other conserved charges of QCD into the description of this pre-equilibrium stage. And I think it would also be interesting, and I think we'll soon be in a position to do this, to somehow assess to what extent this linearized description based on Green's functions is actually accurate and applicable to early stages of heavy ion collisions. And in simple theories like the relaxation time approximation, we can actually test that against somehow having numerical nonlinear evolutions. Okay, that's it. Thank you very much.
Thank you very much. Thank you very much for this very interesting talk. And I see there is a question in the chat here from Gabriel Denicol. Please go ahead.
Hi, Sören. Thank you for the very nice talk. So actually, I have a naive question about slide 10. I mean,
slide
when
10,
you showed
let me go back. Yeah. 10, yes.
Yeah, so there's this formula up there. So you show some relation between T min u at some given time tau, and then T min u at some given time tau 0. Mm-hmm. So I thought in a microscopic theory, it's not sufficient to know T min u at a given time to determine it at a later time, that you need more information. So here's any other approximation, like small wave number or?
No, this is an excellent point. This is an excellent point, of course. So, I mean, what you have to do in practice, I mean, at the end of the day, we do this based on the kinetic description, right? So what you have to choose is you have to choose some initial condition, right? So you have to associate some delta F, if you want so, with that particular perturbation of the energy momentum tensor, okay? And I mean, what we do is we do this in a physically motivated way, right? So for instance, the perturbation of the energy, we essentially take a scale derivative of the distribution function and say that's what's causing the fluctuation in the energy, right? Or if we have a velocity perturbation, we do a little boost, okay, of our background. But that's true, okay. I mean, in principle, you could consider different, so to say, initial conditions which give you the same, macroscopic perturbation, and you could study the sensitivity on that as well. Yeah. And I think we may have done that in the context of Young-Mills kinetic theory. I don't know if Alexas is around and can comment on that. But that's, yeah, I mean, we haven't, so in this, certainly in this work, we haven't looked at that. We just chose something that we thought would physically meaningfully represent this particular perturbation. Yeah.
Okay, thank you.
Okay, I see a raised hand from Mike Strickland. Please go ahead.
Hi, Sören.
Hi.
I had a question about the simulations including quarks. So is this essentially using Alexis's code that includes the quarks, or how are these results generated?
So this is using our own code that that includes
Separate
quarks inclusions, right? Yeah.
Mm-hmm.
So what the code, I mean, but yeah, I mean, it's leading order QCD kinetic theory. Okay.
Mm-hmm.
What's different from previous implementations is that essentially we treat all light flavors as explicit degrees of freedom. So we have separate quarks and anti-quarks, which also then allows us to go to finite density. But this calculation here on the left, in principle, where one just varies the initial chemistry, that should be the same outcome if you run Alexi's code. Yeah.
So because it seems related to something that Alexis and Dekra and I are working on, where we try to extend this analysis that we did for pure glue for all of the moments of the distribution function. And so maybe we should have some discussions offline about the overlaps.
Yeah, yeah, we probably should.
Okay.
Okay, are there any further questions?
I have a question, but as an organizer, I cannot raise hand. Maybe I can go ahead.
Please do.
Do you understand some features of this response in the expanding background using the analysis of singularities of the retarded correlator in equilibrium? I mean, there's a paper by Paul Romachka from.
Yeah, I know. So I know. Yeah, no, I know the paper that you're referring to. I mean, to tell you the truth, I haven't thought about this actually. So how would you actually use that in this context?
May I make a comment on that regard?
Yes, absolutely. Go ahead.
I mean, unless Sören has something to say, I prefer to wait. Don't worry.
I mean, well, I mean, let's put it like that, right? So I mean, in a sense, right? What you could probably learn is something about like this structure, right? Like whether I mean, what does the structure look like, say, at late times or something like this, right? What you'll certainly not learn anything about is how it depends on, I mean, on evolution type, so to say, right? Because W tilde is, so to say, really characterizing the non-equilibrium evolution, right?
Yeah, I mean, I was just curious to see if you have thought about it.
Yeah, now Maurizio can make his comment. No, but I mean, the part of the reason that, you know, I was sort of talking about this or advertising this is, I mean, I would be happy to have sort of further insights into these objects because I think they're very interesting, and so
Yeah,
it was really meant as an encouragement for other people to also look at these things.
There is work in progress on that direction. So that's the first thing that I have to say. We don't have still yet the final answer. But the second thing is that the calculation of pole was done in a static background, and this background that we are working here is the expanding one, and there are some additional issues that introduce certain problems in order to treat them like in the complex plane in the way that you have in mind. And you have to deal with those issues of the branch codes and the poles in a very particular way. So there is work in progress, but I don't have an answer completely yet, and I am not so certain how much this picture originally drawn in the article of Paul and later on by other people, how it works in this expanding system. I don't have the answer yet. But
yeah, I mean, certainly, if I may weigh in, right? I mean, certainly an important difference is, I mean, this is a non-equilibrium problem, right? So you cannot that easily somehow Fourier transform with respect to time and look at the structure.
That's a problem that is correctly what you say. The main problem is how you map the information in the Fourier transform, and in the approach that we have done in our papers with resurgence and so on. We never use the language of mapping into the Fourier space or Borel plane, anything you want. We actually work always in real time, and that's why we can really work at the level of the differential equation. And we are using the same strategy here in the upcoming work. And well, let's hope to see. Once we have the final answer, I will tell you, but we never work in when you have these non-equilibrium problems, it's really hard to do those techniques, and we prefer just to stick to some techniques that we have learned and developed also, which show Alireza, Thomas, Vladi, Hao Cheng, and Nicolas.
Well, very good. Do we have any further questions? We're actually about to finish on time if there are no more questions. And I think there are no more. So I think the organizers have foreseen now some kind of